All right, so today we get to finish up chapter 23, and we're going to talk about diazonium salts and a couple of new reactions. You guys are familiar with working with diazonium salts. You guys actually made them in lab when you did your diazo dye synthesis. However, I did want to bring up a couple points that students tend to get confused on. The first is comparing these two molecules. This one we've got 3 oxygens around it versus this one where we only have 2 oxygens around it. What's the molecule on the left called? It's HNO3. Nitric acid. Super strong acid, common in labs. If we look at the one next to it, it sounds similar, but it's called nitrous acid. So if you remember back to your Gen Chem prefixes, the ic versus us designates differing oxidation states for that nitrogen. When we're making diazonium salts, we do a similar reaction to what we saw with nitric acid. If you remember, with nitric acid, we could treat this with sulfuric acid. So we protonate that alcohol, it can kick off, and then we form our nitrosonium ion, right? That was when we talked about electrophilic aromatic substitution. And if we try to do this with nitrous acid, we get a similar reaction where we protonate that alcohol and then it can fall off. But this time we form a nitrosonium ion. So if water falls off, you could have nitrogen with a positive charge. Let's put in some lone pairs here too so we can do formal charges easier. All right, so we've got 2 lone pairs on that oxygen. If we look at this nitrogen, it's got a positive charge. This is resonance stabilized, right? And so we can actually take electrons from this oxygen, clamp down, and we can get a nitrogen-oxygen triple bond, where now this oxygen has that positive charge. This could be a good ACS question. Which one of these do you think is the major resonance contributor, and why? That's the big thing that people get hung up on, is they want to look at the electronegativity. That is important, but octets take priority. So if we look at the one on the right, it's got full octets on every atom. That means that this one's going to be our major contributor, even though we're forcing oxygen to have that positive charge. So this is our nitrosonium ion. Let's take a look at the mechanism really quick. Most of you guys have already done this on your problem of the day. First thing we do is we get some sodium nitrite. Which is the salt of our nitrous acid. And then we're going to treat this with another strong acid, and traditionally this is done using HCl. First step, the oxygen will grab a proton from HCl. We'll turn that into an alcohol, so now this is a neutral molecule. And in the second step, we typically have excess HCl around, so we'll just protonate it one more time. Now we've got this really nice leaving group. This leaving group can just fall off. And now we've formed this nitrosonium ion that I was talking about, where we know it's resonance stabilized, and it's actually in between a double and a triple bond. Whoops. Sorry, my pen's not happy here. There we go. And now this oxygen has the positive charge instead of the nitrogen, and we've kicked off water in this reaction. All right, and we know these nitrosonium ions tend to be quite reactive due to the positive charge, and we've seen them react with amines already a couple of times. So let's do a little bit of review. So reactions with nitrosonium ions. And this, if you remember, is our nitrosonium ion. All right, we're going to break this down into reaction types. The first reaction we're going to look at is with primary amines. So we're going to take sodium nitrite, just like we saw above. And the reaction I showed above, I showed it with one-way arrows. However, I don't know why my eraser's not working. However, it's really an equilibrium reaction. So we'll dump in some HCl, and we'll form a little bit of our nitrosonium ion. I'm just going to draw one resonance structure. However, you could draw both if you really want to. And then in the next step, we're going to treat this with our primary amine. And this primary amine will attack that nitrogen, and then we'll kick up electrons onto that oxygen. Actually, this eraser thing's driving me nuts. I must need new batteries. Come on. All right, so we've got a nitrogen-oxygen double bond now. And then we've got the other nitrogen that's covalently bonded to it. So this nitrogen now has a positive charge. All right, what's the next step for this reaction? What was it? Yeah, we've got to do some proton transfers. You guys saw that in your problem yesterday, where you grab a proton. These are typically done just in aqueous conditions. And then you form an equivalent of hydronium in this reaction, at which point your oxygen will grab that proton from hydronium. So we're just going to do some proton transfers. Now this oxygen's got a positive charge. And then in the next step, water's around. So water will come grab this remaining proton on the nitrogen. The bond between it will get clamped down, and then we'll kick electrons all the way up to that oxygen. So now we've got a nitrogen-oxygen single bond, a nitrogen-nitrogen double bond, and we've reformed our hydronium. In the next step, this oxygen is going to pick up another proton from the hydronium. Now this oxygen has a positive charge. And then what do you think will happen next? Got a good leaving group. Is it just going to fall off on its own? Yeah, it's going to get pushed off. A lot of students try to draw this where the water just falls off on its own, but that will violate the octet rule on that nitrogen and make it really unstable. So it's a lot easier just to take some of these electrons and push it off in one step. So now you've got a nitrogen nitrogen triple bond. We know this internal nitrogen is going to have a positive charge. And then you've got water as your leaving group. Does that make sense? The other thing to remember too is we also have chloride floating around. That was the conjugate base. So if we look at this, this entire thing together is called our diazonium salt. All right, let's do the same thing with secondary amines and see how they differ. We've seen primary amines a couple times already. Yeah, sorry. This reaction with secondary amines is more interesting. So let's do the same thing. Is it okay if I scroll up? Sure? All right. All right, so with secondary amines, we first take sodium nitrite, so NaNO2. We'll react this with HCl. We'll get a little bit of our nitrosonium salt. But this time our amine only has, whoops, my arrow's going the wrong way. My amine only has 1 proton on it instead of 2. Shoot. Come on, Microsoft, work with me here. So we've got HNR2, that can be any alkyl groups coming off of that amine. This time our amine is going to attack in, kick up electrons. And water can come, deprotonate it like we saw in the previous reaction. And when you do this, you end up with what's called a nitrosamine, specifically an N-nitrosamine. Why doesn't this reaction proceed any further? Good point. This reaction won't proceed any further because if we start doing more proton transfers, we'll violate octet rules at some point. So you get stuck at this N-nitrosamine. All right, let's take an example of this reaction and let's try to predict what the product will look like. Okay, in this example, we've got this compound, and I'll draw in the stereocenter just to be specific. And we're going to treat this with sodium nitrite and HCl. Which nitrogen do you think is going to be more reactive?
Well, it would break aromaticity, right?
Yeah, well, if we think about the lone pair on pyridine, right, it's in an sp2 lobe kind of sticking out. If we look at the lone pair coming off of the other nitrogen, it's in an sp3 lobe. It's sticking out much, much further. It's got more P-like character. So the nitrogen up here is going to be much more reactive than the nitrogen coming off of pyridine, right? So what will our product look like if we treat this with nitrous acid? We'll make this a quiz question worth 5 points. How many of you guys think you got this one? couple people. Okay, so let's just go back up and look at our mechanism really quick too. If we look at our mechanism, that amine, all we're really doing is adding an NO double bond onto the amine where the hydrogen used to be, right? So it's as simple as replacing that hydrogen with an NO double bond. So let's go back down and fill this in. We're going to replace this hydrogen right here with an NO double bond. And we'll make sure we've got our stereo center all drawn in. And there we go. Does anybody recognize the molecule on the left from biology classes at all? This is called nornicotine. Like, oh yeah, it was on the tip of my tongue. So nornicotine is found in tobacco plants. It's one of the major bioavailable nicotine sources. One big problem, as many of you guys are aware, with smoking is that it's really, really bad for your lungs, specifically because of this reaction. So whenever you react nicotine with getting completely tongue-tied. Whenever you do a reaction with nicotine and your nitrosonium salt, you end up with this highly carcinogenic N-nitrosamine. So specifically, this functional group over here causes all sorts of problems in your body. Most N-nitrosamines are known carcinogens, and they're really, really bad for you. Another common source that people get exposed to N-nitrosamines, I have terrible news, is in bacon. So if you ever see meats where it says nitrates added, and you start heating it up, you actually get this reaction to occur at secondary amines on amino acids in bacon. So try to keep your bacon intake to a minimum. I know, I had a student last year, he's like, I don't care if it causes cancer, I'm still eating bacon. Fair enough. All right. So let's take a look. Don't go and like report that to the news. But cured meats and bacon, at least fried bacon, has been linked to an increased amount of cancer. However, like with most things, the dose determines the poison, right? It's a similar thing to like if you smoke one cigarette when you're 14, you're not going to die of lung cancer probably. But if you smoke every day for 80 years, there's a pretty good chance you're going to develop some sort of cancer. All right. Oh yeah, somebody was asking me about this the other day, and they're like, what about vaping? That's a really good question. And if you've been watching the news lately, the FDA is starting to regulate vapes a lot more, specifically because it's a black box. People don't know what's in a lot of the e-juices that are in vapes, and there's been a lot of suspicion that there are some pretty nasty things in there. So vaping, I would argue, isn't a safe alternative. It's an unknown alternative. So just something to keep in mind. Johnny.
I was going to come give you a battery for your pen. I'm not going to
Sorry, I had to pick on you.
Tell me you're recording.
I'm recording this. It'll be on YouTube forever. All right, so if we look at alkyl diazonium salts, do you have a? Oh, you do? Well, now I feel bad.
You should feel bad.
All right, so if we look at alkyl diazonium salts, you can make alkyl diazonium salts from a primary amine, right? So we saw that reaction. However, these cause a lot of problems. What do you think a major problem with alkyl diazonium salts is? Not cancer, close. Any other ideas? Explosives. If we think about this, this can pop off dinitrogen really easily. Anything that rapidly evolves a gas is considered explosive. So you'll generate a bunch of N2 gas, and if you look at what we're generating as a byproduct, you're generating a carbocation. And so let's make a little note. These are super unstable. Why are they unstable? What will happen to this carbocation?
Be attacked by oxygen.
It could be attacked by other nucleophiles. It could undergo methyl shifts, hydride shifts, alkyl shifts, you name it. These alkyl groups, when they are cationic, are quite unstable and will do all sorts of reactions that you don't want them to. So alkyl diazonium salts just simply aren't used very often because A, they're explosive, and B, they're too hard to control. So let's just write a little note. These are not synthetically useful. I suppose so. Yep. To be perfectly honest, if you pulled this out of a freezer and probably shook it, it would explode. A lot of these are shock sensitive, and they're unstable except at really, really low temperatures. All right. This brings us to aryl diazonium salts. With aryl diazonium salts, we saw that we can make these from aniline derivatives. You guys did this on your pod and in lab. So we form our diazonium salt from aniline. The cool thing is that these are quite stable. You can make them. They won't necessarily explode if you take them out of the freezer. And then you can functionalize these really easily. So there's a whole class of reactions based off of the functionalization of diazonium salts. And I'll show you guys a handful of them. The first one, what we're going to do is treat this with copper chloride. And what that will do is swap out that dinitrogen for a chlorine. So you can make chlorobenzenes really easily this way. So you can convert that NH2 from an aniline all the way into a chlorine. The next one is with copper bromide, where you can form bromobenzene. Similar reaction. And then you can see where this is going. Copper iodide. And then last but not least, we've got copper 1 cyanide. And so you can actually convert this into a nitrile. All of these are classified as Sandmeyer reactions. And the aryl halides in particular are really useful intermediates because you can do organometallic chemistry on them and a bunch of cross-coupling reactions. Our textbook doesn't really get into that, but if you go on and take higher level organic chemistry, you'll see these reactions on a regular basis. So let's take a look at the mechanism really quick. The mechanism's a little bit unusual because it involves metals. All right, so the first step of the mechanism simply involves that dinitrogen popping off. However, it actually pops off in a radical manner. So we've got a positive charge here. What we're going to do is pop one electron over to that nitrogen. So we have to use a fishhook arrow. And then the other electron is going to pop over to the carbon on the benzene ring. So you end up with, whoops, let me put it on the right position. You end up with benzene that's got an unpaired electron. You've got dinitrogen, and then you also have copper plus floating around in solution, so it's copper 1. Copper 1, if you're familiar with its oxidation states, can shuttle between copper 1 and copper 2. In fact, copper 2 salts are more stable than copper 1 salts. So copper is more than happy to give up an electron, right? So copper is going to give its electron to that nitrogen. Will form dinitrogen gas. It's no longer got unpaired electrons, and will form a copper 2 salt. So that's the first step in the mechanism. The second step is, now that we've got benzene with an unpaired electron, that can react with a halogen, or really any sort of group where you've got a negative charge, whether that's a cyanide or not. So I'll have X minus. And then during this reaction, you're also going to lose an electron, right? So I'll do minus E minus. And by doing this, you're able to append a halogen onto benzene. And then what do you think's taking that electron? Copper. So copper in this case is going to be converted back into copper 1. So it'll be just regular copper plus. And if you think about that, the halogen that's coming in has 2 electrons. You've got 1 electron on the benzene, so one of those electrons has to go somewhere. It's going back onto that copper. We're not going to get into the whole organometallic mechanism beyond this. This is just kind of our simple explanation of what's going on. Does that make sense? What's that? The X minus?
Yeah.
Yes, the X minus will attack at the site where the radical's on. There are some Sandmeyer reaction variants that are pretty cool. So let's take a look at a couple of these. Let's say we've got our diazonium salts. And we treat this with water. And we crank up the heat. What do you think we could maybe turn this into? Not everybody all at once. An alcohol, right? Water can act as a weak nucleophile. If we really crank up the heat on this, you can actually convert this to a phenol. If you remember back, I think it was chapter 19, we were able to make phenols through elimination addition reactions and a couple other ways. However, we said in order to do that, you have to crank up those reactions to upwards of 300 degrees Celsius. This one requires much more gentle conditions. So this is a nice alternative to high energy chemistry. So let's make a little note. To nucleophilic aromatic substitution and elimination addition. There's also another variant that I think is pretty neat. You use this diazonium salt, and you can actually pop it off and just replace it with a hydrogen. We have to use a special reagent for this reaction. We use hypophosphorus acid, that's a mouthful. So H3PO2, hypophosphorus acid. And this is a really nice way of just exchanging out that diazonium position for hydrogen. So I'll show you guys in particular why this is such a useful strategy for synthesis. So this is a cool trick. What happens if I treat benzene with Br2 in excess and iron tribromide? What do you guys think?
It's going to add bromine.
It's going to add a bromine once, all right? And then the first bromine, is that going to be an ortho-para-director or a meta-director? Yeah, it's going to be ortho-para. So what we'll likely end up with is 1,4-dibromobenzene. But let's just say, for the sake of argument, I don't want 1,4-dibromobenzene. I want 1,3,5-dibromobenzene. So the question is, how can I get that regiochemistry? I can't do it using traditional bromination techniques because we know that will orient them para to one another. But what we can do is get a little bit tricky. So let's take a look at a workaround. First thing we need to do is get that NH2 group installed on the benzene. How could we get an NH2 group installed on the benzene? Can we do it directly? No, but we can nitrate it, right? So first thing we'll do is nitrate this. We'll go NO2. That means we need nitric acid and sulfuric acid. And then how can we get this to be converted into an aniline? Yeah, HCl and zinc, or HCl and iron, or hydrogen and palladium on carbon. Either one of those will work. All right, now that we've done this, we know that aniline's a really strong activator. If we brominate this, what we end up doing is over-brominating in the ortho and para positions because this electron system is so rich. Now what we need to do is remove that NH2 group, right? So the workaround that's clever in this case is we first turn this into a diazonium salt. So NaNO2 and HCl. And now we need to remove that diazonium salt and replace it with the hydrogen. How can we do that? Yep. So we're going to use H3PO2. And now we're able to get 1,3,5-tribromobenzene rather than 1,4-dibromobenzene. So it's a pretty useful workaround for that sort of chemistry. All right, I think we have one more major reaction with diazonium salts, but we've already seen these before. So I'll go through them somewhat quickly. These are our azo-coupling reactions. All right, so the first thing we're going to do in our azo-coupling reaction is form our nitrosonium ion. And then in the next step, we're going to react this with some sort of aniline. And if you remember, this aniline was just going to kick up electrons onto that oxygen. Now we've got an nitrogen with a positive charge. And do you guys want to see the full mechanism of the diazonium salt, or do you guys want me to shortcut it? Raise your hand if you want me to shortcut it. All right, looks like we're going to go through the full mechanism. So this was what you guys did on your pod, right? I gave you guys an aniline. Water will come grab this proton. Now we've got our neutral molecule. We've got hydronium, and this oxygen will come grab a proton from hydronium. So now this oxygen's got a positive charge. And we've regenerated water in this reaction. This water can come grab the remaining proton on that nitrogen. It'll clamp down, kick up electrons to that oxygen. So now we've got a nitrogen-nitrogen double bond. We've got hydronium floating around. This alcohol, again, will grab a proton from the hydronium. Oops. There we go. Got 2 electrons here and here. Oop. And now the next step is going to involve the electron from that nitrogen clamping down, and we'll kick off water. So we formed our diazonium salt. The cool thing with the diazonium salt is we can react this with another benzene ring. So I'm going to show another benzene ring in a different color. And specifically, I'm going to have an OH group coming off of here. One thing with this reaction is you've really got to make sure that the benzene ring you're reacting with in the second step is very activated, meaning it has a strongly electron donating group on it. So this should be electron rich. So it could have an OH group, it could have an NH2, it could be an anisole, it could be any sort of combination of that. And the reason being is this para position right here, the one on the opposite side of the ring as your electron donating group, is going to act as your nucleophile. It's actually going to attack that nitrogen and kick electrons over to the nitrogen next door. So now we've got both of these benzene rings coupled together. However, the position that attacked has a positive charge on it right now. Or sorry, the position next door, excuse me, has a positive charge on it. So the last step in this reaction will involve water re-aromatizing these molecules. So this water will grab this proton, clamp down, and we'll get our diazonium, or sorry, our azodi. And as we saw in lab, these azodies are quite colorful due to the conjugation going across both of the benzene rings. All right, I think what we're going to do is hold off a little bit here. We'll do some synthesis practice on Monday just because we're running out of time. But I did want to present awards for the synthesis project. So I got Elsevier gift cards. All right. I guess we'll start with the best report. If you would like an Elsevier gift card, you can grab one. If you would prefer an Amazon gift card, let me know and we can swap out the Elsevier gift card for an Amazon gift card. All right, best report. The top prize goes to Van. Van went through and got the actual ACS guidelines for submitting a formal report. So Van went above and beyond. Ramon is also one of the best report winners. He also followed pretty strict formatting guidelines. And then Ung as well. She got another perfect score on her lab report. Do you want an Amazon gift card or Elsevier? Amazon? All right. Fair enough. All right. So those were our top 3 best reports. I couldn't pick just 2 this year. The next one goes to highest yield. Highest yield, I had to kind of do some digging and make some judgment calls because a lot of people reported above 100% yield. So if you did report above 100% yield, you got scaled down to 100 because I refuse to believe that you can make it matter. The top award goes to Shakiba, who got one of the highest yields. Do you want an Elsevier gift card or Amazon? Amazon? And then next up was Min. Got one of the highest yields too. Do you want Elsevier or Amazon? Amazon. All right. And then last but not least, we've got our Lemon Award, meaning your reactions didn't go smoothly in the slightest. And I think we had a 3-way tie, so again, I had to award an extra one. Raquel had to redo 2 of her reactions, but you ultimately got product, right? Yeah. And then the other 2 were Brandy and Holly, who also had to redo their reactions multiple times. But Brandy, you got final product, right? Yeah. And then Holly tried really hard. All right. Do you guys want Elsevier or Amazon? Elsevier. All right. All right. Thank you guys for your hard work. I'll see you guys on.